All right, so Faraday's law, blue. So Faraday's law, what it gives us is it gives us a way to generate electricity in a sense that EMF or voltage is equal to minus and then N times the change of the magnetic flux with respect to time. And now keep in mind that the equation for the magnetic flux is A times B times the cosine of the angle between A and B. And then just so that you understand what this thing is, EMF is it's just voltage, and units are volts. So, or at least you can think of EMF as voltage. For all practical purposes, that's fine. So, couple things that come out of this equation. You can then take these two equations and combine them into the following, where this is minus N times delta of A times B times the cosine of the angle theta, and all of this is divided by the time. And sometimes I give this to the students as the equation, but then well, anyway, so there's that. Now there are a couple things you can do with it. So here's the first option, is that EMF could be minus N times, well, maybe it's just the area that is changing. So times B times the cosine of the angle theta. That's possible. And then B and angle theta are constants. The second option is that you could have EMF equals minus N. Maybe it's the magnetic field that is changing. This is the first problem we did. That would be delta B over delta T times the cosine of the angle theta. And then A and theta are constants. And then the third option you could get is that the EMF equals minus N times A times B times the change of this whole function cosine theta over the time. Now the last one is perhaps the trickier, because you can't just, this is not the same thing at all as minus N times A times B cosine of the change of the angle theta over the time. That is not the case. You can't do that. That it just doesn't work. For those of you who have had some calculus, delta over delta T is the derivative with respect to time, and so you can't just do this. That simply doesn't work. Instead, what it is minus N times A times B. You will actually have to write a whole cosine function, cosine of theta F minus cosine of theta I divided by the time. These are the three options. These are the three types of problems you could get with Faraday's law. You're going to get either changing A, or you're going to get changing B, or you're going to get changing theta. Right, but if it's the theta that changes, then you have to do it in this way. Now let's see if we can consider these three cases and sort of make sense out of them. So let's slide this whole screen to the left, and let's look at the first one. Let's make some room here. I don't need this. I need this here. So conceptually, let's see if we can make sense out of it. The first case was the one where we have a changing A, that the area of the loop is changing, and so in that case, the equation for EMF becomes minus N times delta A over delta T times B times the cosine of the angle theta. Well, let's see if we can figure out how that would actually happen. So suppose you have a magnetic field, and the magnetic field points into the page like this. And then let's say that in this magnetic field you put a loop that looks, you put a loop that is, let's say, fairly big. What loop do I want? let's take a square loop. So we have a square loop here in this field. Looks like that. And then let's say that the same loop somehow is shrunk. So we have magnetic field at points like this. And what we do is we take the same loop, but we manage to shrink that loop so that it looks now like this. It's just smaller. Now, how exactly would we do it physically? Well, you could take a, here's what you could do, in case you're wondering. You could take a loop that runs like this, right? And now it has a certain area because of the radius here. And then let's say you pull in this direction, you pull in this direction, and as you pull, you end up with a loop that is much smaller because now the radius here is smaller. So it's not that difficult to make this happen. But we don't need this picture here. Let's get rid of it. And let's see what happens to these charges. So I have charges here, and these charges sort of sit on the side. Oh, I gotta fix something, 1 second. Okay, so I have a bunch of positives here. And I have a bunch of positives here simply because this is a wire made out of atoms and all atoms have charges. So I have charges here. In reality, it's the negative charges that flow, but we consider the conventional current. So it's we're doing it as if the positive charges were flowing. And as long as this loop just sits here and there's nothing interesting, there will be no force on these charges, right? These charges have to move in order for the force to actually show up. Well, what will happen is if I go from this to this, then I can see that the this wire here would have to move to the left at some speed v. This wire would have to move down at some speed v, this wire would have to move to the right at some speed v, and this wire would have to move up at some speed v. And then if every single one of these wires does that, then I will end up with this loop, which is smaller, and now I have the charges that are packed here. And I have charges that I have here, charges that are here, and charges that are here. Let's consider what's happening with what force do we have on these charges as they move. And so let's use the right-hand rule. Right-hand rule here, magnetic field points into the page, velocity is to the right, therefore forces on these would point down. Forces on these would also point down. Wrong. Forces on these would actually into the page right. Forces on these would point up. Oh, that's good. Forces on these here would let's see. So force points up. Magnetic field points to the page. V is up. Force here would be to the left. So the force here would be to the left. That's really good. And then on the top here, I would have the force pointing to the right. So by the right-hand rule, as these charges move down, the force points to the right. As these charges move to the left, the force points down, and so on. Note that these forces here are aligned, and I would get a current. It's going to be a current flowing in this loop here because of the forces present. And so I'm going to end up with a current I that flows like this. So if you change the area of the loop, you will end up with current. And if you have current, then you have to have voltage. All right, so this equation makes sense. You change the area, whether you increase it or decrease it, you will end up forcing charges to flow. Let's take the second case. The second case was the changing magnetic field. So let's try that. I'm going to move this up a little. That should do. So here's the second case where we have the changing. Now we have a changing magnetic field, and that's going to give us the following equation: minus n times a times the changing magnetic field over the time times the cosine of the angle theta. So a is a constant, area of the loop is constant now. The angle between A and B stays constant, but the magnetic field itself is changing. So suppose that I have a loop, and my loop now points my loop looks like this, right? Where a vector points straight up like that, 90 degrees. This is the a vector. And then let's say that I have a magnet, and the magnet sits below it. So here's the magnet. Here's the North Pole, and then somewhere down here there would be a South Pole. And what this does is it sets up a magnetic field that points like this, points like this, and it points like that. So there's a certain magnetic field that points through this loop, into this loop, and then through this loop, right? So this should go on and continue, and this should go on and continue, and so should the middle one go on and continue up. There's magnetic field that points through this loop. They have that and this and so on. Okay. Now, as long as the loop here stays the same distance away from the magnet, the magnetic field through the loop doesn't change. But suppose now that I take this loop and I move it up. So I take this loop and I move it up at some speed v, so that this loop itself is moving upwards at speed v. Then what I would end up with is that the magnet stays here with a North Pole, but the loop itself ended up being somewhere here. And if that is the case, then my loop now is going to be, let me give it some a vector. If this is the case, then my loop is now going to be farther away from the magnet. See here, the loop was this far away from the magnet, but now the loop is this far away from the magnet. It's obviously the magnetic field through this loop is going to be weaker. And so I have the magnetic field here that is now weaker. It still points through the loop, but the magnetic field is now weaker because of the distance. So there's a magnetic field here, but it is smaller. Now you may have, oh, actually, let me redraw it. I think it'll make it easier to see. So let's keep the same shape of the magnetic field. Magnetic field pointed like this, and then it just went out like that. And then here it pointed like this, kind of goes like that. And then here it, let's just extend this. And then this thing goes up here, kind of this, and then this is what that one did. Maybe I'll put one more here. So as you move this loop through the magnetic field, it started here. As you move this loop through the magnetic field such that this loop moves up at speed v here, then you end up moving these positive charges which sit in the loop through the magnetic field. And if charges move through the magnetic field, there will be a force on them. Right, these charges here, the positive charges in this loop here, they will move through the magnetic field, and as charges move through the magnetic field, there will be force on them. And note that the charges will not move in a direction that is parallel to the magnetic field, right? Because the magnetic field here curves. And so it makes sense to see that if the magnetic field is, here's the magnetic field, if the magnetic field is changing, then you will end up with some current flowing because of the force, and if you have current, you will end up with some voltage. Right, so changing magnetic field will generate a force on the charges, and then the force on the charges will generate a current, and then current will, well, if there is a current, then there must be a voltage, must be EMF, some kind of there must be some push on the charges coming from somewhere. Of course, that push comes from the force, and it's the force that generates this EMF. All right, so we have the second case. Now we see that it is reasonable to think that if the magnetic field is changing, then there should be a flow of charges and therefore EMF. The third case is where the angle itself is changing. So let's maybe we can do it here. So the third case, now let's just move the whole screen up. Finally, the third case is that there's a change in the angle. And that gives rise to the following equation where we have minus n times a, area is constant, magnetic field is constant, but now what's changing is the angle itself, angle between a and b. So keep in mind that this is the angle between a and b. So we could probably do it like this. If you have a magnetic field and it points to the right, and then you put, so here's the magnetic field is constant. This is constant. And then you take a loop, you draw a loop here. And now let me think for a second, because maybe I can actually make this loop rotate. Yeah, here, I'm just gonna draw it like that, like this. So here's a loop, and then this loop has vector A, area is constant, so I'm just gonna put here that A is constant. A is constant, we're not changing the dimensions of the loop. But what we will do is we're going to take this point here, and we will move it up, like that. And we will take that point and we'll move it down like that. So we're going to make this whole loop rotate, so that if the A vector was pointing like this at first, then it's going to, now it's going to move and it's going to point like that instead, so that we rotate this whole thing. Now let me get rid of that and let's just keep it like that. So if this loop is in fact rotating like this, then obviously what's changing is the angle theta is changing, because that's the angle between A and B is different now. In fact, suppose that we, the final product is that the magnetic field points here. Final product is that this loop looks like this. Right, so before what we had is that the A vector points in this direction, and now what we have is that the A vector points like this. So we have changed the angle theta. We haven't changed the size of A, we haven't changed the magnetic field, but we have changed the angle theta, angle between A and B. Consider what happens to these charges. So you have a charge here in this wire that sits there, and then charge here and here. You have these positive charges all over the place in this wire, and you have them there because you have atoms, and all atoms have charges. Now, if this charge here, Q, moves down with the wire, speed v, then there's going to be a force acting on it. And if there's a force acting on a charge, then the charge will move. And you could actually use the right-hand rule to figure out in which direction this thing will go, but that's whatever. We'll get back to determining the direction of the current later in different video. For the moment, it should be sufficient here for you to see that if the charge moves through the magnetic field, then there's going to be force in it. Therefore, there should be a current that will come out of it. So there's going to be some current that will flow in this circuit here. So if the angle itself is changing, there's a change of the angle, then that implies that there's going to be a force. And if there is a force, then you will end up with current. And if you have a current, then you have some sort of an EMF or voltage present in this. And so it makes sense to say that changing theta gives rise to that. All right, so let's go back to where we were in the beginning, which is here. Faradays Law gives us a way to figure out what voltages we can set up by putting a wire in a magnetic field. And this is really it. This is the law, but then you can rewrite it in this fashion, and you can end up with these three formulations. So in the next video, we'll do a simple problem with, I think, each option. Although that's not quite true, because we already did this, so that's done. We just have to do this, and then we're good to go.